Thanks very much indeed. Well, thank you, Colin, and thank you very much indeed for inviting me. I have to confess to feeling a slight sense of trepidation walking into this lecture theatre. First, because it reminds me of doing my PhD quite a few years ago, and I thought I'd escaped the academic circumstances, but here we are back again. Secondly, I first came to Surrey University when I was a trainee at the BBC, and it was such a long time ago that when they sent you off to make a film, I was working on Newsnight, you know, the late night news program, and I was sent here to Surrey University, and I had to shoot my film on the day. I was only given the story in the morning, take it back to Shepherd's Bush, to Television Centre, edit it, and then it got transmitted that night. And it's just a 5-minute story, I think, on a satellite that had been designed here at Surrey. And the tricky thing was that in those days, there was no video. So it was shot on film. It was shot on reversal film, and there was a laboratory at Television Centre where the whole thing was processed, took about an hour, and if you were lucky, your film came out, and you then had to go and cut it in the cutting room that day. So technology has moved on, I'm pleased to say. Very helpful so that I can calibrate this talk if I knew a bit more about your sort of experience as astronomers and people interested in astronomy. If people who are on Zoom could possibly give their replies in chat, but I'd just like to ask a couple of quick questions. First of all, can I ask if you have a telescope? Right, well that I'd say is over half the people here, which is very impressive. How many of you have had occasion to take photographs through your telescope as opposed to just observing? So I'd say at least a third. And that's of the people in the audience. I'm going to ask Martin in a moment to give us an opinion from Zoom. And lastly, if you have actually studied astronomy at some level. Okay, so perhaps a fifth. What are the figures from Zoom, Martin? Three. Three people have telescopes, or?
Sorry, make that 2 and 2. So one is studied, one is not studied.
Okay, all right. Well, I will try in this talk then and not forget the people who are new to the study of astronomy and the practice of astronomy, and I'll try and cover some of the basics as well as the more advanced topics. This is where I'm very fortunate to live, on Holy Island in Northumberland. That's my back garden, and that was early on in my astrophotography experimentation when I didn't have an observatory and I had to set up my telescope each night in the back garden. And those of you who are familiar with this experience will know it's quite complicated because it takes a good hour or two to get the thing polar aligned, and usually cold and so on. But that's a dawn looking east, Holy Island Castle on the right. And I've had a house on Holy Island for about 30 years, but I've lived there full time for the past 5. And I'm interested very much, of course, in the stars and astronomy, but I'm also interested in all aspects of the natural history of Holy Island. And you'll see there's a bit of a theme in my interests. This is my latest project. We've just published it. It arrived on a pallet from the printers about 3 days ago. It's a book on all 170 plants of Holy Island. And I spent the last 2 or 3 years in the day, when I wasn't in my observatory at night, photographing the plants. And so it's a photographic book. Another somewhat insane project I worked on for the last 20 years concerns the periodic table of elements. And I was walking around Holy Island on New Year's Day 2001, and I thought, ooh, I'd like to have a box with 100 or so bottles with a little bit of every element in it. I'll go on the internet, and I looked up this idea, and I couldn't find anyone except for an obscure Russian company that had gone out of business. And so I thought, a marvelous business opportunity. If I knew then what I now know, anyway, in one of my companies for 20 years, we've been manufacturing these things. We do provide a little bottle as full as possible, given cost and nuclear explosions, with all the elements. We do have a piece of every element it's possible to have up to uranium, up to 92. We draw the line at the transuranic elements, but you do get an empty bottle with the symbol on the lid, so at least there's something. Anyway, very complicated project, but notice again, round about 100, 118 to be exact things. And then this has been probably my main activity for the last 20 years. It's working on a digital interactive app version of the best guidebook, European Birds. And that's taken me all over Europe, wider Europe and the Middle East, filming. We have video of 800 European species of birds and comprehensive coverage. So it's rather more than just 100, but again, you can see the theme, collections of interesting things in the natural world. So one evening in my back garden on Holy Island, I walked out, this is about six or 7 years ago, and I looked up and I saw the Milky Way, and I thought, I wonder how many things, deep sky objects there are up there. And you know, if you look with the naked eye, you really can just see stars and the planets and the moon. But with a telescope, and especially with a camera, you can begin to see a family of objects. The more observant of you here will notice at the bottom there, that's the Ring Nebula, a teeny planetary nebula. But it's one of several hundred, if not several thousand, deep sky objects that have been catalogued by astronomers over the last 150 years, or longer in some cases. And they fall into various categories. Top left, that's a shot of the Pleiades taken from my garden in Holy Island. Likewise, the Andromeda galaxy, you'll recognize, I'm sure, and its satellite galaxies, small ellipticals nearby. Galaxy groups. This is an object I don't think many of you will have seen unless you've been to Australia or South Africa or South America. It's a southern object, probably the most beautiful, colorful area of the sky. I'll talk about it in a bit more detail later on. Some of you, I'm sure, will recognize that wonderful object, the Veil Nebula, which is visible very much as an object in northern skies. Here we have a globular cluster, and here we have a dark nebula. Again, this is a southern object. That's the Snake Nebula from the southern hemisphere. So those are the main categories of objects. And what I decided to do is to embark on a project to make a book, and as Colin kindly suggested, please come and have a look at it later, that's essentially a catalogue of all these objects that is a bit like a field guide. And here you can see slightly more enlarged images of the Pleiades and a globular cluster, the Veil. That's Rho of Fucci area, southern object, and it's a fantastic, you could almost say there's everything in there, including the kitchen sink. It's got a dark nebula, you can see dust clouds streaming at the bottom. It has bright emission nebulae. It's actually got, if you look very carefully there and there, it's got globular clusters, star clusters within it. Here is another beautiful northern target, the Elephant's Trunk Nebula, IC 1396, I think. And it's, again, an emission nebula that you can't see through the lens of a telescope, through the eyepiece, but you can see very well if you use a camera and expose for several minutes. You can pick up the nebulosity. And what we're looking at here, you can see it's a more or less a spherical shape. And that's actually the outer shell of an explosion that's in slow motion expanding. It's expanding too slowly for us really to see it move much, even in a whole human lifetime. But it is an explosion several million years ago, a star, a supernova, and we're looking into the center of that explosion through clouds of dust. And the reason the edges of the circle are denser and apparently more fuller of nebulosity is because we're looking through the edge of the sphere. We're looking through more of the sphere. And there is another wonderful northern target, very, very good object to photograph. It's visible all through the year, very near the northern celestial pole. It's the North American Nebula, so called because that, I think, is meant to be the Gulf of Mexico if you stand on your head and squint. Now, I'm sure you recognize this. It's the most photographed object in the night sky, the celestial equivalent of Piccadilly Circus, I suppose, or Trafalgar Square. It's the Orion Nebula. And I'm often asked whether the colors that you see in these kind of images are real. And the answer I usually give is yes, they are, in the sense that they genuinely represent structures in the sky. And many people are surprised when I say that you actually take photographs of these objects in black and white. The best astronomical cameras are very high resolution, and to achieve the highest resolution, they use monochrome sensors. So it's a black and white image. And in order to get those colors, what you do is you take a succession of photographs through filters. And this carousel is a bit like a sort of Gatling gun on the back of your telescope. And these glass filters here, they go between the telescope and the camera. And you can instruct, using a computer, the wheel here to turn very accurately from position to position. And you can see that there are 7 filters. That's the standard number you tend to use for taking these pictures. One of them is just a clear filter. I think it's probably number 1. I think it's that one probably. That's basically just like a UV filter you might put on the front of your DSLR, and it cuts out ultraviolet and some infrared. But then you have red, green, and blue, which are the filters that correspond to our cones, our color sensors in our retina, in our eyes. And using those red, green, and blue filters, you can take a picture of a structure in the sky that's close to what you would see if you had very, very sensitive vision and could float in space in front of it. The other 3 filters, these are the silver ones down the bottom because they're mirrored, are special narrowband filters, and they are sensitive to the emission of different elements in the stars and in the nebulae. There's a hydrogen filter, an oxygen filter, and a sulfur filter. And when you take a picture, this is what you get. So if you remember the color picture here, this is actually a perfectly matched hydrogen filter image. And if I go to the next one, that's the oxygen signal. And there is the sulfur. And by combining the 3 together, by assigning different colors to each of the 3 channels, you get a color structure. Now, the actual choice of colors, there's some conventions, there's certain palettes that you can follow. NASA uses what's called the Hubble palette, which this is a variation of, where blue is assigned to oxygen and typically red or orange is assigned to hydrogen. So the colors are showing you where different clouds of gas with different preponderances of elements are. So there is sort of sense to it. Dark nebulae are, in fact, not structures that are immediately the result of explosions. They're the ashes and dust clouds left over from explosions. And here's a marvelous object, the Shark Nebula, visible again in the Northern Hemisphere. And it's absolutely enormous. If I was to put the moon into this shot, it would be about that size. It's a huge thing, which is over our heads, many times when we look up in the night sky, but we don't realize it's there because our eyes are not sensitive enough to see it. So when we take these pictures, we have to take very long exposures. A typical exposure for a narrowband picture would be about 5 minutes, 300 seconds. And you don't just take one, but you typically take a dozen, even in some cases 50 or 100. And the reason for doing that is you're chasing high signal to noise ratio. So you can take 100 pictures of, let's say, the hydrogen filter's view of Orion. In a computer, you can stack them, and the computer will then reduce the signal to noise ratio to produce a lovely image at the end of the day, like that. Another trick that you play with astronomical cameras, that those of you who have them will know, is you actually have a fridge built into them, a Peltier two-stage cooler, and it will cool the sensor of the camera down to about -25. These days you don't need to go quite as cold, but that also helps to improve the signal to noise ratio. It basically reduces the thermal noise and means that the light signal that you're collecting, the photons from the distant astronomical objects, have a better chance of showing up against the noise. So galaxies, I think the object in the sky that gives me the greatest level of astonishment. This one on the left, the pinwheel, is very like we think our own Milky Way. We're located just on the edge in a spiral arm. But galaxies are many, many distances away. If the objects in our Milky Way, for example, if we consider ourselves the Earth here in Guildford, then a typical object in our own galaxy, the own Milky Way, our own Milky Way, might be somewhere in London, central London, the furthest part of London from here, north, the very north M25 would be on the far reaches of our galaxy, and then objects which are much closer to us would be in South London. But other galaxies which we can see outside the Milky Way, they would be in Rio de Janeiro. So that's the sort of scale. We know that in a typical galaxy, there may be as many as 200 billion stars, other stars. So in our own Milky Way, we're one of 200 billion stars. And in all of the other galaxies that we can see, we think there's typically 100 billion or so. There's the Andromeda galaxy. That's actually one of the closest galaxies to us, which is why we get such lovely pictures of it, because it's relatively large in the sky. Again, it might be surprising for some of you to realize that the moon is about that size. So Andromeda is really a huge object. And it's racing towards us and is going to collide with our own galaxy, the Milky Way, but not for a while. We've got 1 billion years or so. And astonishingly, we think when it arrives and the great collision happens, almost nothing will happen. The stars, the galaxies are so far apart that they can actually, two galaxies can actually pass through one another. It's not totally true, because what they will do is have enormous gravitational influences on one another. So in fact, we can expect our own galaxy and Andromeda to be perturbed, and tails of stars will be thrown off over celestial time. But there'll be very few actual collisions of stars, which I suppose is slightly reassuring. Now, this is my favorite picture I think I'm going to show you tonight. It doesn't look very spectacular, but wait. It is something called Markarian's chain, and it's a group of galaxies discovered by the astronomer Markarian. You can see that there's a sort of string of them here. I guess if you were to squint and look very carefully, you might reckon there were what, something like 20 or 30 galaxies visible there of different kinds. Well, I've got a piece of software, an amazing piece of software called PixInsight, and you can feed a photograph like this into PixInsight, and it will identify every point of light, and it will then draw triangles between each of those points of light in its, in its head, as it were, and measure the angles inside the triangle, and then take all those numbers, and you're talking of tens of thousands of numbers, and look them up in an index. And the index is all the objects that astronomers over the last decades have catalogued. There are catalogues published of galaxies, and it will then label the galaxies that it can see. So the next slide I'm going to show you is this same picture, but with the labels applied to show the names of the galaxies done automatically. And when you see this next picture, I want you to remember that each of these small galaxies in the frame that you can see here contains 200 billion stars. Now that is a patch of sky not much bigger than your thumbnail, held up at arm's length. And actually, although Markarian's chain is an attractive group of galaxies, you could point your telescope anywhere in the sky at night where you're not looking through the dense Milky Way, and this is what you get. In every direction, as far as we can look, there are galaxies, and innumerable galaxies, and these are only the ones we've named. And some of you, I'm sure, have seen one of the first pictures taken by the James Webb Space Telescope, or JWST, and it's a much more powerful telescope than the one I used to take this. And that telescope covers a patch of sky that is the size of a grain of sand held at arm's length. That's the field of view of the JWST. And the picture is exactly like this, just as many, if not more, because the optics are so good, galaxies there. So it's in Enrico Fermi's brilliant question, if you know the Fermi paradox, the physicist who helped to invent the nuclear bomb, where are they? Why haven't we been visited by or seen alien intelligences if there's so many potential places? We now know, of course, that over half of the stars have planetary systems going around them, and we think possibly as many as 1 in 10 stars have habitable planets. So interesting question. Anyway, it brought me back to this. I thought this is a wonderful meat, wonderful subject matter. Let's make a field guide to. We chose 110, the 110 best things to see in the sky, and we chose 110, as I'm sure some of you will recognize, in homage to Charles Messier, the great French astronomer who catalogued objects in the night sky, and he had 110 in his catalogue, so that's why 110. And this is the book that we produced. It's called The Visible Universe, and our goal really was not to try and produce the best photographs ever taken. We couldn't possibly do that. We're not good enough astrophotographers, but we wanted to show people the sort of photographs that you can take with reasonably accessible equipment if you take care. And so that's what this book is. It's a catalogue of the 110 best things to photograph in the night sky, and the best things to photograph not just from our hemisphere in the north, but also, as I'll explain in a moment, from the southern hemisphere. And I did the project in partnership with Charlie Bracken. And I teamed up with Charlie because I'd read, in order to get up the learning curve, the very steep learning curve, I bought his marvelous book called The Deep Sky Primer. It's now, I think, in its 4th edition or coming up, but it was in the 3rd edition or 2nd edition when I met Charlie. And he's by day a mild-mannered marketing executive for a big pharmaceutical company, and at night he turns into a demon astrophotographer, and he's incredibly talented. He's a physicist by background, and he's written quite a few books, actually, of which The Visible Universe and The Deep Sky Primer are only 2. My own background, as I mentioned at the very front of the talk, was working in the BBC. I was in the science department for most of the time and made quite a few Horizon films, if you know them. And then I got involved in the BBC's very early digital experiments, and led a management buyout of a group from the BBC and went into publishing. And we published a lot of apps, that's really my background. I also, very late in life, went and studied chemistry. So I've got a bit of science training now. So in the book, we have these 110 objects. We divide the sky into 8 sections. And then for each of the objects we choose, you can recognize again the North American nebula I showed you earlier, we usually have a full page picture of it. And then on the right-hand side, Charlie's written some very helpful text if you want advice about the best way to photograph these objects. We often show a detail of the object or what it looks like with different filters, the ones I showed you earlier. And then at the top, you can see a chart that shows when that object is visible at different times of year. And in the case of this object, you can see it is actually visible throughout the whole year, but it's best in September, October, November. That's when it's highest in the sky. That's when you have the most hours of taking images. And the different colored lines here, I should explain, they're for people at different latitudes. So there's a code at the top, because if it's an object which is visible from the very far north, then if you're living somewhere on the equator, you'll only see it for less time, and vice versa. We also have, for people who are seriously getting into astrophotography, pages and pages at the back of the book where we give all the magic exposure details, what equipment we used, how long we exposed for, and that sort of thing. So that sometimes that information is hard to find. So it's useful to have it in a condensed form. But what I'm going to tell you about really for the rest of this talk is this image, which is the one that took us far and away the most time. And it is the entire visible universe in one photograph. Now, of course, you can't actually point a camera and take a picture like that. What you have to do instead is create a mosaic. And so this is actually a composition of 10,000 separate photographs that we've combined in the computer. It's not got 10,000 panels in it. As you'll see in a moment, it's only got 153 separate panels. But for each of those panels, as I was saying earlier, you have to take multiple photographs with each filter. So if you do the multiplication, 153 times 7 filters times, I don't know, at least 40 sub-exposures per panel, that's where you get to the 10,000 figure. Now, what you're looking at here is actually the Milky Way. That strange arc is the Milky Way. That's the center of the Milky Way, the fiery burning heart with a black hole in the middle that you can't really see from our northern latitude. But the Milky Way, of course, doesn't have this funny shape. The reason it looks like this in this picture is because we've applied a projection to get what is a complete 360-degree inside of a sphere onto the printed page. It's the same as the Mercator projection that you use in an atlas, where Greenland and Antarctica are very distorted. Well, so too that happens here. And in fact, if you look at the bottom, you can see that there's some lines here, which are in fact at the poles, individual stars that get splayed out into lines. But the data we've got is the whole of the inside of that sphere at very high resolution. And it's reduced considerably here. I think in the next slide, you can actually take that region and look at it, and you're beginning now to see how detailed the digital image is. And I'm actually working at the moment now on taking this data, because it's an enormous data set. It's gigabytes and gigabytes, and putting it into a headset, one of those virtual reality headsets, so that you can be inside that data, almost as if you're floating in space, and you can look around, and it's very, very exciting. So it's not very easy to program, but so this is where I live. This is Holy Island in Northumberland, and it's I don't know if anyone's visited or been there. It's unusual. It's a small community of 150 people, visited by 650,000 people of tourists each year. But we have the marvelous tide that rises and falls, and when the tide comes up, most of the tourists leave, and so we have the island to ourselves. I do have a video which I normally play at this point in my talks to show extremely rash, stupid drivers going along the road to Holy Island, because you can only get onto the island when the tide is out, and there's a road that lets you get on, and then the road comes up, and there are big warning signs. But it's one of those things, thank goodness, where there isn't a kind of barrier that comes down. You just leave it to people's common sense. Or not. The best one, actually, if you're interested, go to YouTube and Google Holy Island driving disasters, and you'll find an Uber driver who was just following his sat-nav and drove straight through the sea. Quickly. Indeed. I think there was probably an electric car as well. But Holy Island's actually rather a good place. It's just here, halfway between Newcastle and Edinburgh, and it's astonishingly dark. It's actually Bortle 1, for those of you who know the Bortle system, which is as good as it gets. So from that point of view, it's ideal. And so excited by this prospect, and full of enthusiasm for astronomy, I rushed and built an observatory, and there I am proudly in my observatory. It's a Takahashi 106 telescope above me, a pier, everything, sliding roof, rolling roof. But it turned out, after quite a few months of bitter experience, that there's some snags to astronomy on Holy Island. One of them is my beloved cardoon on the right here, which I'm very loath to cut down because it's very good for insects and bees. And it quickly grew up to eclipse many astronomical targets. So that was very bad. Secondly, Holy Island is quite far north. And in fact, I'm sure you know about astronomical darkness, which is the very darkest part of the night, which happens about an hour after civil twilight. You eventually get to astronomical darkness, and that's when you can take the best photographs. But on Holy Island, from early May through to late August, there is no astronomical night. We're too far north. So in winter, it's great because we get very, very long nights. It's dark by about 3:30 in the afternoon and stays dark till 10 in the morning. But in summer, for 4 months, I can't take any photographs at all. So then my observatory becomes a greenhouse, and the tomatoes curl up the telescopes very happily, but it's not very good for productivity. It's also, as I was saying, incredibly dark. And when I look out of my back view, I normally see absolute blackness if the moon is not out, if it's the new moon, apart from 2 pinpoints of light. One is a lighthouse on the Farne Islands that flashes once every 20 seconds, and the other is a navigation buoy in the North Sea. Apart from that, I cannot see any light at all until one terrible evening in the autumn of last year. I drew the curtains, and this is what I saw: an appalling light pollution suddenly destroying the pristine darkness of Holy Island. And this is the culprit. It was Northumberland County Council refurbished the public toilets on Holy Island and modeled the design of lighting on Colditz prison camp, or possibly a casino in Las Vegas. And these lights were on from dusk at 3:30 in the afternoon until dawn, completely destroying and ruining all hope of astronomy. So fortunately, I have a column in the Holy Island Times about astronomy once a month, and I waged a gentle campaign to shame the council into restoring, and God bless them, they fitted these marvelous special astronomer-friendly downlights, and the problem went away. So that was all right. But then there's this problem, and this is the one I think is insuperable. On this chart, you can see lots of red squares, and that's when it's cloudy. And the green squares and the yellow squares are when it's suitable for taking, well, it's the green ones anyway, for astronomical pictures. And I'm sorry to say this is actually quite typical. So I think on a very good month, I get 3 or 4 clear nights a year. And if you're trying to photograph all 110 objects and take 10,000 photographs of the entire celestial sphere, I once calculated it would take you 8 lifetimes on Holy Island to do. So by very good fortune, just at the time this problem was arising, British Telecom and Openreach arrived, a huge fleet of vans appeared, men and women jumped out with yellow jackets and spent 3 days cabling Holy Island with fiber optic cable. The fact that Dominic Cummings has a house on Holy Island is totally unconnected, but they did fit fiber optic to everyone's door. And so this opened up the possibility of remote astronomy, trying to find places where I could put telescopes that had much better weather. And I like the look of this. This was for the same period as you saw Holy Island. This is the weather forecast for a wonderful observatory in the middle of the Chilean Andes. And you can see, I've had a telescope there now for 3 years, and the average number of completely clear, beautiful nights is 300 nights a year. And I mean, it's just absolutely mind-blowing. And the quality of the sky is fantastic. So this is a place called Deep Sky, Chile. It's 20-kilometer drive off the road to get to up a mountain. No tarmac, very rough road. And in the middle there is Frank Jobard, a marvelous Frenchman who has really, with one French partner who does the IT and is based in France, Frank has built this. When I was here in 2018, a year before the pandemic, it had 2 of these vast sheds, you can see, easily the size of this lecture theatre, with a roof, enormous roof that comes on and off. No cabled internet, no electricity, no water. So they have solar panels, enormous batteries. And now he's got 6 of these. And he is what's called a hosting facility. And it's a bit like a kind of dog kennel for telescopes. You can take your telescope and he'll look after it. If something goes wrong, dear old Frank gets up at 3 in the morning and hopefully sorts it out. And he's got that horrible drive. Now, that's actually my telescope there on the right. I've got two telescopes in Chile now. This is the one that we use to take that picture of the whole universe. And it's actually quite small. Frank always reminds me of this fellow. I don't know if any of you recognize it, but this is Klaus Kinski from Werner Herzog's incredible film, Fitzcarraldo. And it's a true story of a rubber baron from the early part of the 20th century who decided to take a steamer over a mountain in the Amazon in order to reach uncharted rivers where he could harvest rubber. It always reminds me of building a telescope on and hosting facility on top of a hill. Sorry, I just put that in. And here's just one example of the appalling hardships. This is a very cunning seed dispersal mechanism for the cactuses that live beside the rough track for 20 kilometers going up the hill. And those spikes are about 6 inches long, and the cactuses merrily cast them off. And so when you're driving, you have to go about 5 miles an hour, scanning for any of these things, because they'll go through the tires, easily pierce the tires. It's particularly unpleasant, actually, when you're coming home exhausted from fiddling with your telescope and having polar aligned, which does your brain in. And then you have to drive 20 kilometers at night, going very slowly. Now, there you are. Those are the tires that get pierced. We have one neighbor. That's my telescope in there, in that little building there. That's the Deep Sky, Chile. And over there, can you just see a white pixel? Well, that is the incredible Vera Rubin Observatory, which you're going to be hearing a lot about over the next years and decades. It's the National Science Foundation and Chile's amazing new telescope. I'll try and be very short, but just to give you the headlines. It's got a mirror the size of this wall, 8 meters across. It weighs about 300 tons. It can slew from one place in the sky to another in 5 seconds. It takes a picture about an enormous field of view, many times bigger than the moon, in 15 seconds. And it's basically going to photograph the entire southern night sky, every clear night, 300 a year, with a camera that's the biggest camera ever built, and it's the size of a car, and each frame is over 1 billion pixels. And it will send that data in real time to tens of thousands of astronomers around the world who have signed up to get the data stream. And it will use artificial intelligence to scan each frame as it comes in. It takes about 2 weeks, I think, to photograph the entire sky. So it will go back and look at all the previous frames of that same patch of sky, and it will flag any differences. And it's looking for differences. And a difference could be due to an asteroid, moving through the sky quite fast. It could be due to a supernova in a distant galaxy that suddenly flashed on, but maybe only for a few minutes, so normally it's missed. And it's thought, for example, to take supernovae, I think in the entire history of observing for the last 1,000 years, we've managed to see and actually photograph about 60 supernovae. I think I'm right in saying that. And it's thought in the first year of operation that the Vera Rubin telescope is going to have something like 300,000 detections of supernovae. And it's basically going to be able to map everything in the solar system bigger than a washing machine. And it's incredible, absolutely incredible. Anyway, they put it here for a reason, because the sky is very good. So I think it was very fortunate that we're there. This is the Vera Rubin telescope. It's almost finished. Another year of commissioning. They haven't put the real camera on yet, but the lens, the mirror is in there. And that's what the Milky Way looks like. That's not a bit of Photoshop. That's an actual, probably a 60-second exposure with a DSLR of what the sky is like there. Just fantastic. That's my second telescope. I've got a Takahashi 130 that I operate remotely there. That's the camera for the wide field images that we took. And you can see it's a rat's nest of cables. It's very, very complicated doing remote astronomy. For those of you, I know some of you in the audience, Colin has got a system in Spain, and you'll probably recognize the sort of labeling that you need to do to have any hope of, in the dark, putting the whole thing together. There are essentially 6 critical components in a system. There's the telescope itself, of course, but in many ways more important than the telescope. And if you're going to buy an astronomical system, this is where you should spend the bulk of your budget. The mount that moves the telescope and positions it very accurately, and then keeps it tracking very accurately on a star. That's an incredibly important piece of equipment. Then you have the filter wheel with horribly expensive filters that go in there so that the black and white camera can take the color pictures. Then you have a focuser that super accurately focuses each image. The whole focus story is complicated. The telescope that I use, the small one, actually does have a DSLR lens. It's currently got a 135 millimeter telephoto lens, and that's absolutely great for doing astrophotography. This is a particularly fine one that needs to be focused by turning the grip in the way that you would focus yourself. But of course, you're 10,000 miles away, or however far it is. So you have a cogwheel, a nylon cogwheel that attaches, and then a stepper motor with another cogwheel, and that's what does the focusing. But of course, you can't do what you can do with the naked eye and observe the stars going in and out of focus. For one thing, you're not there, but more importantly, the stars are so dim that you wouldn't have any hope, even if you were there with the naked eye, to focus that way. Instead, you have to take a typically 5-second or 10-second exposure, and then you get the computer to measure how big the star is. It chooses a bright star in the field, and it measures how fat the star is, and then it turns the cog a little bit and takes another picture and measures how fat that is. And that's what this graph is showing you on the left. The y-axis up and down is how fat your chosen star is, and the x-axis across the bottom is the position of the focus wheel. So basically focusing in and out. And what you want, this is a very nice focus curve, as it's called. And you can see that it's a parabola, and at the bottom, the stars are smallest. And that is where everything is in focus. Unfortunately, you can't just do this at the beginning of the night and then wait, hoping that it'll stay in focus. The focus drifts. And typically in Chile, the temperature drops by maybe 5 degrees between dusk and dawn. And that's enough for the metal in the telescope to contract ever so slightly and put your focus way out. So you essentially have to repeat this process about every half an hour through the night. It's a challenge. But there's a view looking up under that small telescope. The challenge, of course, is to plan a campaign of photography to take all 10,000 pictures in the course of it took us 18 months to do that. And there's such delights in the southern hemisphere. This is the Tarantula Nebula in the Large Magellanic Cloud. This is photographed again in narrowband, hydrogen and so on. That's the biggest globular cluster that we can see from Earth, Omega Centauri. I think something like 500,000 stars in there, and it's an object within our own galaxy. Very old, very ancient globular clusters. There's a full frame view of the marvelous Rho Ophiuchi. I won't talk further about that, we spoke about it earlier. And that's the sort of view I get on Holy Island with my fiber optic connecting to the telescopes. I use a marvelous bit of free open source software called Nina, N-I-N-A, highly, highly recommended, absolutely superb automation. It handles all the many, many complicated things that you need. I hadn't finished going through my list of critical bits of equipment, but there's another 4 or so. You sometimes need a guider. You need heaters to stop the dew forming on your lens. I've got a little flap that in the day I can close, and it stops dust getting on the lens in the day. It doesn't stop it at night, but at least it's 50% better. And millions of other things too. So there's the mosaic. That's a little fragment of the image I showed earlier of the whole universe. And here I think I've got something like 1, 2, 3, 4, 5, 6 by 3, 18 panels overlapping. And you have about 10% overlap. And then the brilliant computer programs like PixInsight or Astropixel Processor, they will seamlessly overlap, get rid of the joins, if you like. It takes hours and hours and hours to process, and it increases exponentially as your mosaic gets bigger. So we had some incredible challenges. That's a recent one we shot in Chile. I think that has 27 panels, and that's the whole of the Large Magellanic Cloud with the Tarantula Nebula in the top there. And we're looking into another very close nearby galaxy, and all the funny blobs and structures you can see here, each of these are nebulae within another galaxy. It's an incredible image, really, to see the richness of structure, and each of these is an exploded star in the process of expanding away. So that's the challenge we had to take that photograph. 153 panels, if you do the maths, is what it takes to cover the whole Earth. But actually calculating where to put them is tricky, and Charlie started off doing it by hand and very rapidly realized that he needed to write some special software to work it out, because the real problem occurs at the poles where your brain will rapidly explode if you try and work out that. This was what he eventually sent me, which is the whole universe covered with 153 shots. But it's not as straightforward as simply deciding, okay, well, I'll go out this evening and photograph panel number 1, and tomorrow I'll do panel number 2. As I'm sure you know, half of the panels can't be photographed from anywhere, any one position on Earth, because we don't ever see the southern part of the universe. We only see the north, and conversely, someone in Chile will only ever see the southern hemisphere. So we had to have 2 systems. So I also set up an identical system in Spain at the excellent EI facility near Seville. So we had 2 identical systems, but that's not all. You also have to take into account the seasons. So at this time of year, half of the universe is blocked by the sun because it's blindingly bright. You can't point your telescope in that direction. You have to wait for 6 months until the Earth has gone round, and then the nighttime sky will be pointing in that other direction. So we needed a very complicated, this is 1 page from what we called our playbook, and it had about 60 pages in it. And for every panel, Charlie worked out how many hours of clear sky there would be if in principle, and how high in the sky, how many hours that panel would be above the horizon. And the green is where there's no moon and you have lots of hours, because another factor is that the moon is a terrible source of light pollution, and you can't take generally red, green, and blue pictures when the moon is up. You have to do that at new moon. So anyway, very complicated problem. But that's the result. This is printed on the inside of the dust jacket. So if you have a look at the book later, take the dust jacket off and look inside. And it's basically the hydrogen alpha channel in black and white, just showing you where the gas clouds are. And you can see the heart of the Milky Way is very dark. And you can see the 110 numbers for our chosen targets positioned. So this overview of the whole universe, we use in the book as a kind of framework to orient you and show you where everything's located. And on the left and right, you can see the list of the objects that we've selected. And the constellations are written in here too, to give you a bit of orientation. Orion, I showed you that Orion Nebula picture. That's here. And you can see there's actually 6 or 7 or 8 really beautiful targets around there. Rho Ophiuchi, that very colorful area, that's here. Down is south, of course. The Magellanic Cloud, there's 2, the large and the small. They're way in the south, very near the southern poles. So I certainly, when I was starting astrophotography and astronomy indeed, I struggled to understand the relationship between all the different objects, where they are in the sky. And so this is very much an attempt to give you a bit of orientation. And there's the final picture combining red, green, blue, and hydrogen. We've actually still got all the data for oxygen and sulfur, but we had to lie down after doing RGB and hydrogen. It is unbelievable how much processing it took. Very, very complicated. So that's basically what I wanted to tell you about. I have bought, we printed 1,000 copies of the book, and I'm very pleased to say we're down to the last 100. So we only have a few left. I bought a few here if anyone's interested. I've got very bad news for you, and that is I can take credit cards. I've got an app on my phone that will do it. So if any of you are looking for a Christmas present for an astronomer, I couldn't think of anything better. And I've also got 3 posters of the, it's actually the color, but with the constellations written on. I've got 3 posters, and we're selling the book for £10 off the Amazon price. So it is genuinely a better offer than Amazon, and the posters are 25. So thank you very, very much indeed for listening. If anyone has any questions, if there's time, I'll be very happy to answer them now or later. And if people on Zoom, thank you on Zoom, have questions, I'd be happy to.
Thanks so much. Okay, Nick.
Thank you, that was absolutely superb. What sort of process do you use to process it?
I did almost all the processing on a Mac.
1 second.
But quite a powerful one. An i9 in those days. The new ones with Apple Silicon would do it even much faster. And I had 64 gigs of RAM and a huge SSD. I think all the data for all of the 110 objects, all the source raw subs, and all the data for the a big celestial image take up about 14 terabytes.
How much overlap did you need between the north and south panels? Is it still 10%?
10%, yes. All the panels are about 10%. Yeah. We did irritatingly have one little hole we discovered right at the end where I typed the wrong number in wrong late at night. And
I noticed you said you're in the Bortle 1 area, but the clear outside.
yes, that's because clear outside goes to the nearest postcode, which is Holy Island Village. But if you go, I'm on the edge of the village, so technically, as long as the council toilets are behaving themselves, I can get. But Chile is Bortle 1, and Spain is Bortle 1 to 2. The thing that makes the real difference in Chile is actually the laminar flow of the air that goes over the Pacific and is not disturbed by any mountains because it's coming from the west generally, and that's it goes over the top of deep sky Chile and then hits the higher mountains in the Andes and breaks up. But until then, you're looking through a very, very smooth layer of jet stream. El Nino screwed things up a bit this year. In fact, we had a lot of rain.
What are your views suitable for a family audience on the so-called mega constellation?
This is Elon's hordes of satellites. Yes, and in fact, lots of people are putting them up. Well, what I'm going to say is very unfashionable. I'm not too concerned. I am concerned as an aesthetic person, appreciating the night sky, and the fact that that experience will be ruined for so many people, just as an observer, visually, I think is a great shame. To their credit, they have been trying to mitigate the problem by painting them black and orienting them quite carefully. But the reason as an astronomer or astrophotographer I'm not too concerned is twofold. First of all, the problem only really occurs at dusk and dawn when you're in darkness on the ground, but the satellites overhead are in sunlight. And during most of the night, that's not the case. You still have the constellations flying over you, but they're in darkness and you can't see them. But the other reason I'm not too concerned is because of a marvelous checkbox in PixInsight, an astropixel processor, which you turn on when you do your stacking. I think I told you you typically take 50 subs of a particular bit of sky. And you'll find that although many of the 50 subs have satellite trails going through, they're all in different positions. And this checkbox is called outlier rejection. And it's a statistical algorithm that's applied to each pixel in the image. It looks through all 50 subs. It says, right, I can see that 48 of these are the same, and 2 of them have got a satellite trail, and it will reject those. And actually, it doesn't reject the whole sub, it just rejects that pixel. So you keep most of the data, even from a frame that's covered in musketry. So it's actually, it's a problem, I think, that can be got around.
Do you think, you mentioned that you were forced to abandon the terrors of Holy Island to go to very convenient Chile. Do you think actually that remote hosting will sort of kill UK-based astrophotography?
I still need my observatory in Holy Island because that's where I prototype and test and refine and learn, and it's hands-on. And you can't do that with a remote telescope system. I should have mentioned that there's a wonderful network of telescopes called iTelescope that I expect some of you will know, that anyone can sign up, and for fairly modest sums, you can rent their telescopes by the hour. And they have some in deep sky Chile, they have some in Australia, they have some at EI in Spain. And they're a fantastic way to get a taste of taking your own pictures. And probably for an outlay of say £100, you could take plausibly a dozen of the sort of photographs you saw tonight. So it's fantastic to have access to something like that, particularly if you don't have to buy and build your own telescope and ship it out, because that obviously does start getting expensive. So iTelescope is an excellent way to get started. And in fact, in the book, I think probably 20 of the 110 images we photographed with iTelescope equipment. It's all mentioned in the back.
You're taking black and white pictures through different filters. Can you actually combine more than 3 photos through different filters?
Yes, channels is the term.
Because I was thinking,
yes.
presumably, at the end to display on the screen, you've got to map it to red, green.
Yes, but you can achieve marvelous subtle color effects when processing is a whole lecture in its own right, if not a series of lectures. But for example, a very common palette, as it's called, is red, green, blue, and hydrogen. And that's what the big color version of the universe uses. And that gives you the natural colors of the stars, but it also shows the nebulosity. So it's a lovely combination where you get to see the explosions and dust clouds and so on, but you also have the realism of the star colors and the color of the Milky Way. There's a whole this marvelous website.
Because you've only got 3 colors on the screen when you project it.
Well,
so you've got to map it to red, green, or blue.
yes, I mean at the end of the day, but then that's all we can see. But you can bring out the tonality of different structures by using the data from different filter channels to map to different colors that the humans perceive as different. That's what we're trying to do. It's a fascinating mixture of art and science, I think.
Any more questions?
Any YouTube?
Anything from the
I mean, from Zoom?
Nothing on chat, unless anybody had something.
Someone at the back.
John?
Just one as a third, I always take the Collins with me on.
Oh, good.
When will the app be?
Oh, the app has been out and it's available not only for the iPhone, but for Android. Yes, and we've just updated it to the 3rd edition, which was an appalling amount of work, I can tell you, doing the
But that's
proofreading.
the whole of Europe.
Yes, it is. Yes, there is I think we do a British version as a subset, but because so many of the best birds are European vagrants, I'd highly recommend the European one.
Is Charlie on Zoom?
No, he couldn't, unfortunately. He's working.
It's actually just during the day.
Yeah.
Yeah. Any other questions?
So now you've got a fibre optic link to Vera Rubin.
Oh, yes. And I'll be woken up at night saying, "Is it supernova?" And then 5 minutes later, it's a supernova.
And did you say that you were having one of your telescopes up for sale soon? So if anybody wants to buy one?
Oh, well, I've actually run out of things to photograph in Chile with one of the telescopes. It's been there for 2 years. And I mean, I could photograph boring bits of sky, but I've photographed all the best ones. So I'm thinking, Colin, you might be interested. So if anyone would like to come and see the book, I've got an open copy here, so please do come and have a look. And I'll also take the poster out if anyone at all would like.
Well, thank you very much.